Hi, everyone. Have you ever wondered how computers make decisions? It all starts with simple logic. Let's learn about logic gates. Before we get into this video, let me introduce myself. My name is Jordan Cristiano Tampi. My student ID number is 2510110600076, and I am the creator of this video. What is computer logic? In any computer system, every logical operation strictly follows the input-process-output (IPO) model. Input is the raw data that enters the system. In the world of computer logic, this is simply a stream of binary signals, a 1 or a 0. Process is where the logic happens. The system uses logic gates like and, or, and not to evaluate the input based on predefined rules. Output is the final product, the logical decision generated by the process. It is also a binary result, true, 1, or false, 0. In essence, every task a computer performs, from the simplest to the most complex, boils down to this fundamental cycle. It accepts input, processes it with logic, and delivers an output. Types of logic gates. Let's now meet the three fundamental logic gates that form the backbone of digital logic. And, or, and not. The AND gate acts as a strict enforcer. It only outputs a 1 if all of its inputs are 1. If any single input is 0, the result is 0. The OR gate is much more permissive. It outputs a 1 if at least one of its inputs is 1. It only gives a 0 if all inputs are 0. The NOT gate, also called an inverter, performs a simple but crucial task. It reverses the input. A 1 becomes a 0, and a 0 becomes a 1. Combination of logic gates. We can combine basic logic gates and, or, and not to create more complex gates. These gates are known as universal gates because they can be used to build other logic functions. Let's look at three main examples. 1. NAND gate NOT AND. This is an AND gate followed by a NOT gate. This gate produces an output that is the exact opposite of an AND gate. While an AND gate produces 1 only if all inputs are 1, a NAND gate produces 0 only if all inputs are 1. For any other combination of inputs, it produces 1. 2. NOR gate NOT OR. This is an OR gate followed by a NOT gate. It inverts the output of the OR gate. While the OR gate produces 1 if any input is 1, the NOR gate produces 1 only if all inputs are 0. This is an all-off detector. 3. XOR gate, exclusive OR. The XOR gate is more selective than the OR gate. It means one or the other, but not both. This gate produces 1 only if both inputs are different, one 0, the other one. This gate produces 0 if both inputs are the same, both 0 or both 1. Logic gates in the real world. Logic gates are not just theoretical concepts. They are the basic building blocks of the electronic devices we use every day. They enable our gadgets to make automatic decisions. Here are some common examples. Automatic doors and lights. When a motion sensor detects someone, input equals 1. It triggers the door to open or the lights to turn on. Output equals 1. This is a simple input-process-output action. Calculators. Every mathematical operation, from basic addition to complex functions, is performed by a complex combination of logic gates that process binary numbers. Home security systems. These systems rely on combinations of logic gates. For example, an alarm will sound output equals 1. Only if a window sensor is triggered and the system is active, a classic use of logic. Essentially, logic gates are what enable computers and smart devices to process information and take action automatically, making our modern, automated world possible. Now you know how computers think using logic. Don't forget, all smart systems start with simple logic. See you in the next video.